Good morning. This week we are going to talk about estimating validity. Now, this is the first of two lectures on estimating validity. So recall from our previous work that a test is defined as reliable if the observed score variability is due to true score variability. So in some sense, the scores that you see are consistent across the board. We're going to shift this week to talk about validity. And so to do that, we need a working definition of what it means for a test to be valid. So the one that we're going to use is as follows. A test is valid if it measures what it purports to measure. So that gives you sort of the two comparable yet slightly different measures of what it means for a test to be good. It is both reliable and valid. So this week let's focus on validity. Now, overall, there are often considered to be three types of validity. And we're going to be talking in detail in this course about two of them. The first of these that we're not going to focus on is content validity. So there are a lot of ways to consider content validity. Those are different from the purpose of this class, but in sum, content validity is simply a subjective rating of your test items by content experts. So that tells you to some extent how valid your scale is from the perspective of the content that it contains. What we are going to focus on instead, particularly this week, is the notion of criterion-related validity. And then next week we'll move on to construct validity. So what is criterion-related validity? Well, essentially, criterion-related validity is the extent to which test scores are related to some criterion that you either set or some criterion that you measure and you want to measure the relationship to that variable. So a couple of examples of this, and you'll see how they're slightly different, are as follows. The first is, so for example, in an industrial organizational psychology context. So let's suppose you have a test for screening job applicants. And this test then needs to relate to some criterion of work effectiveness. In other words, you wouldn't want a test that measured something that was not related to work effectiveness if the goal of your test is to screen job applicants and find the set of the best job applicants that you can get. So you want to make sure, you want to measure whether your test actually does predict work effectiveness or work success. Another very common criterion-related validity situation is when you have school admissions tests. ACTs, SATs, GREs for graduate school, etc. So these tests, they're set up to relate to the criterion of academic performance. So maybe something like GPA or percentage of students who complete a program. So again, the idea is that your test needs to somehow relate to this external criterion. So how do you measure the validity that is related to this criterion? Well, in the most simple cases, we simply measure reliability with a correlation coefficient. It just goes back to your Stats 101 type idea of relationship. So this, of course, is denoted rho xy. Now, the common notation that we're going to use is we're going to let x represent your test score. So this is the thing that you're wanting to validate. And y is going to represent this external criterion. And when we see this rho xy, we're going to refer to that as our validity coefficient. So contrast that with the reliability coefficient. The symbols might get a little bit confusing, so make sure that you take a look at what the symbol is, and remember, if we're saying rho xy, that's the relationship between the test score and the criterion score, and that's your validity coefficient. So of course, if we back up just a second, the goal of this lecture is how do you estimate validity? Well, in some sense, there's nothing to do here. You simply have to measure, you have to get your test score measurements, and you have to get the accompanying measurements on the criterion score, and then you just simply compute a correlation. So there's really not that much to that. What we need to talk about is the role that reliability plays in this. So what role does reliability play in criterion validity? Well, this is something that we haven't talked about too much, but now is a good time to bring this up. And that is the following fact. A test cannot correlate more highly with any other score than the extent to which it correlates with its own true score. Okay? In other words, you can't expect a test to be a very valid test if it isn't reliable. Okay? And the equation that we use to describe that relationship is this. We say that rho xy, this criterion-related validity, is always less than or equal to the correlation between x and its own true score. Now, of course, we know that the correlation between x and its own true score is the square root of the reliability coefficient. So in a sense, the correlation between a set of observed scores and a criterion score is always less than or equal to the square root of the reliability coefficient. So that is the relationship, that is one relationship between validity, okay, this guy, and reliability. Namely, validity is less than or equal to the square root of reliability. Now, what can we do with that? Well, we note that if a test does not have perfect reliability, so the reliability coefficient is less than 1, then the validity coefficient is less than what it could be. We say that it is attenuated. And that is a problem, because then that says that what you're really caring about, this relationship between the true scores on the observed variable and the criterion variable, your correlation that you're measuring is always less than that. So that's kind of not good, right? Because we want to estimate this reliability coefficient, but we want it to, this validity coefficient, but we want it to reflect the true score relationships. And so how do we correct for this attenuation? Well, it turns out that Spearman figured this out a long time ago. Spearman proposed the following idea to do this, what you call attenuation correction. And so let's work through what exactly Spearman proposed. Well, first, we note that by definition, the correlation between x and y, the observed score and the criterion score, is simply the covariance of those two scores divided by the product of the standard deviations. That's just simply the definition of correlation. Now, I will mention that it is pretty easy to prove that the covariance between x and y is the same as the covariance between the true score components of x and y. You can prove this simply by writing x as true score plus error score and writing y as true score plus error score, and then just simply computing the covariance. And it turns out that they're absolutely equal. So by that simple relationship, we have the following. We have that our validity coefficient, rho xy, is the covariance of the true scores over the standard deviations. So where does that take us? Well, we can then compute the correlation between the true scores, the rho tx and ty, as the covariance of tx and ty divided by the standard deviation of tx times the standard deviation of ty. In other words, just the definition of correlation. Now, from what we just showed, we can write this covariance as the correlation between x and y times sigma x times sigma y. Substituting that in for this covariance, we then get this expression that I'm sort of circling here with my mouse. Now, what can we do with this? Well, if we do a little bit of rearranging, if we simply take the numerator and multiply by 1 over sigma x and 1 over sigma y, we have to do that to the denominator as well. That'll cancel these guys out, but it'll put a sigma x and a sigma y below these sigmas so that you get what's in this line. Okay? So in other words, our correlation now reduces to rho xy over this guy times this guy. Well, why did we do that? Well, this right here, if you remember, this sigma tx over sigma x and sigma ty over sigma y, this looks a lot like the proportion of variance in the observed scores that's due to true scores. In other words, this is the square root of reliability for x, and this is the square root of reliability for y. And so if we write that, we get that the correlation between the true scores is the observed correlation divided by the square root for the reliability of x and the square root for the reliability of y. So that is the formula that Spearman derived in 1904. So what I want to do first is an example of how you would use this formula and perform this correction for attenuation. It can actually result in some surprising consequences. So here's an example. Suppose that test A relates to some criterion C with a correlation of 0.4. And then you have another test, test B, that relates to that same criterion with an even lower correlation, 0.3. Okay? So if we just stop right there and ask which is the more valid predictor of criterion C, we might say, well, test A has a higher correlation. So it seems like it's probably going to be the better predictor for this criterion. But let's keep going. Further suppose that the reliability of test A is 0.81, so pretty decent. But the reliability of point B is really low, only 0.25. And finally, that the reliability of C is 0.64. So the question is, which test, A or B, is the more valid predictor of criterion C? So if we start with this idea that validity is indexed by the correlation between the observed test and the criterion, then certainly the higher correlation, 0.4, would mean that test A is the more valid predictor. But remember, since test A and test B do not have perfect reliability, their correlations with the criterion are reduced, they're attenuated. So what we're going to do is we're going to use Spearman's correction for attenuation to figure out what the true score reliabilities are. In other words, the true score correlations that we would get if we had better reliability, if we had perfect reliability. So we're going to compute these corrected validity coefficients. So for test A, let's start there. So the formula, if we just copy it down, is the correlation between the true scores of A and C is equal to the observed correlation divided by the square roots of the reliabilities. So the observed correlation was 0.4, and then we take the square root of the reliability of A, which is 0.81, and the reliability of C, which is 0.64, and we do this math, and it turns out that the correlation between the true score for A and the true score for the criterion C is 0.56. So we've gone from an observed correlation of 0.4 to a hypothetical potential correlation of 0.56. Okay, so that reflects the attenuation standpoint. The observed correlation is lower than what it could be. Well, let's do this for test B. So the correlation between the true score for test B and the true score for test C, well, we apply the same formula. We plug in the observed correlation between B and C and then divide by the square roots of the reliabilities. We actually get something higher. We get 0.75. So this potential correlation indicates something rather surprising. Even though we have a lower observed correlation, we're getting a lot of attenuation, a lot of reduction in the correlation between the true scores because the test for B is not reliable. So if we could put in some effort to making test B more reliable, and of course we saw last week that simply adding more parallel items will do that, then we can actually get a much higher correlation in the end between B and C than we had to start with. And so what this tells us is that since test B test B has the largest potential validity coefficient, and thus would probably be the better one to invest some time in to predict criterion C. Now this is kind of a tricky question, right? Because what is the best one kind of depends on resources. If you need to use it now, right, certainly the test A gives you a better correlation, so it's probably going to be a better one to do right now. But keep in mind that there is some potential for test B to be much, much better. So that kind of reflects this idea of how attenuation works in the context of reliability. And it certainly affects the potential validity. Now I want to note that one of your homework exercises will talk about this for single variables as well. So for example, suppose you just wanted to estimate the true correlation between a predictor, observed score, and the criterion true score. So not the two true scores themselves, but just the observed score and some criterion true score. Well, then what you do is you simply partial out the reliability of that criterion. What I mean by that is instead of dividing by both the square root of the reliability for X and for Y, you would simply take the observed correlation and divide by the reliability for y? Well, the square root of the reliability. So this phrase that we use, partial out, that's kind of the way I think about the formula that Spearman derived for correcting for attenuation. Let me illustrate that. Well, let me illustrate with the example. You've got the observed correlation for test A and test C as 0.4. Then you need to partial out the unreliability. So that means divide by the square roots of the reliabilities. If you're only partialing out one of the test's reliabilities, then you wouldn't divide by the other one. And that's what this formula is expressing. So keep that in mind. If you're wanting to find the correlation between both true scores, then you need the original Spearman formula. But you can adjust it if you're only caring about one of the true scores. So that's what we would use here. The other part of the lecture, so that's the first half, which is basically the interplay between reliability and validity. The other part of the lecture is kind of a hands-on idea of how screening works. So what does that have to do with anything? Well, one way to think about this is in an industrial organizational sense. So as I mentioned, one of the examples of criterion-related tests is job screening. We often will give people a test, and if they score higher than a certain amount, then they can be put into the job pool, and if not, they don't get in. Same thing with schools, right? So you put people into hire or do not hire categories. You put school applicants into a successful or not successful category. So the question is, how does this work? How does this screening work? Well, the basic procedure is this. What we have to do is we have to set some cut score. And so that is a score on this criterion variable, so that if you score higher than that cut score, that is y is bigger than or equal to z, you put people into one category. Typically we would call that successful. And if they score lower than that cut score, we put them into the other category, the unsuccessful category. So the question is, how do you set this cut score? Or, well, actually, no, let's not go there yet. Let's just see how this works. Okay, so how do we look at validity of such a procedure? So here's an example that we can start with. Let's suppose that we had 100 job applicants that were screened with some test. Now, we're going to put those 100 job applicants into a contingency table. That is, we're going to split people up by their actual outcome and what was predicted to be their outcome. So let's look at the rows first. Let's suppose that of these 100 job applicants, 50 of them would have been successful at their job, whereas 50 would have been unsuccessful. Now, of those 50 who were successful, what did the score say? What did this test say about them? Well, of those 50 people, this test predicted 30 of them to be successful and 20 of them to be unsuccessful. So keep in mind, I'm giving you this information. I'm not just figuring it out on the fly. Okay, this is a table that I have given you, and we're trying to interpret it. So the test, again, just to recall, said 30 of those people would be successful, but it kind of got 20 of them wrong, right? They were successful, but it predicted that 20 of them would be unsuccessful. We can play the same game with the 50 people who were unsuccessful. The test maybe predicted 10 of them to be successful, so that's wrong, but it got the other 40 correct. So what we're going to do is we're going to say, look, you've got 4 possibilities here. You can predict successful and actually be successful. You can predict unsuccessful but be successful, so that's an error. You can predict successful but be unsuccessful, that's another error. Or you can predict unsuccessful and be unsuccessful, so that's true. That's a correct. Okay. So the ways to be correct on this contingency table are to be predicted and actually successful, and to be predicted and actually unsuccessful. Now, if you look here, 30 plus 40 equals 70 out of these 100 were predicted correctly. And so we call that the hit rate, and that's how we index the validity. This hit rate is the proportion of applicants who were correctly screened. So we take that 30 and that 40, and we divide by the total, 100, and we get 0.7 or 70%. So this 70% basically tells us how well our test did at correctly screening our applicants. Okay. Now, I want to notice that this hit rate is good, right? 70% is good, But it's good for a very specific reason that we need to talk about. It's good because it works better than just hiring everybody, right? In other words, do you want, as a company or as an industry, do you want to expend the money and the resources to give people this test when it does potentially no better than just saying, let's hire everybody, or let's not hire anybody, right? If you just take one of those sort of across the board procedures, what's your hit rate then, or what's your success rate? Well, we can see in this table that if we just hired everybody, our success rate would be 50%. And of course, if we just didn't hire everybody, our success rate would be 50% as well. Here, this 50% is something that we call the base rate. Okay, so it's the best hit rate available from all possible procedures. So our test, which we got a hit rate of 70 out of 100, or 70%, is good. It is valid in the sense that it improves on this base rate. We go from basically being a coin flip to whether we're going to get a good applicant or not, to getting now a 7 in 10 chance that we're going to correctly screen our applicants. So that's a good test. We want to improve on the base rate. What would it look like if that was not the case? So let's get another example of this kind of screening procedure. This time, this is not for hiring purposes, but rather for a diagnosis purpose. So let's suppose that we had 100 people who were screened for some psychopathology. Now, let's again look at the actual frequency in the population of these 100 people. 90 people exhibit no psychopathology, okay? 10 people exhibit the psychopathology. So we've got a base rate of 90% that says you're 90% not going to have this psychopathology, okay? So what we want to do is we want to see if this test that screens people improves on that base rate. Well, this test correctly predicts people with psychopathology to have a psychopathology 7 out of the 10 times. And of the 90 people who had no psychopathology, it only correctly screened them 76 times. So it left 14 people here and 3 people here misdiagnosed or misscreened. So what is our hit rate? Well, our hit rate is where things match, right? The prediction equals the actual. So that's 7 here and 76 here. That's a total of 83 out of 100 total, which gives us a hit rate of 0.83, right? So that sounds really good. That's actually a better hit rate than our previous example. But the base rate is 90%, right? Our base rate comes from the fact that we could just categorize everyone as having no psychopathology. So this test that we're giving only hits 83% of the time. If we just told people that they had, if we just said people have no psychopathology, we would hit 90% of the time, right? So this test doesn't work. We would be better off giving no test at all than we would be to invest resources and human capital in administering this test that actually reduces the hit rate. So when you have a high base rate like this, you have to have an even higher hit rate or your test is not worth it. So these two examples exhibit how validity works in this context. Here, validity is not really correlation, but rather it's some sense of did you improve the hit rate? But it's still able to be quantified, of course. So that's how screening tests work in relation to validity. So the last thing that I want to talk about before we're done here is these cut scores. How do you set them, right? How do they work? So let's illustrate that with an example. So let's consider the following score distributions. You can think about this as some job performance score, and we categorize people into successful and unsuccessful. So the question is, which cut score would give us the largest hit rate? Because of course that's what we want. So here's the data. Okay? We'll come back to this several times. If you need to pause the lecture to write this down, that's perfectly fine. So people, let's just see how this table works. So this represents all of your people who took the test. There were 3 people who scored a 20 and they were all successful. There were 5 people who scored a 19 and they were all successful. There were 14 people who scored an 18. 12 of them were successful, 2 of them were unsuccessful. Go down here, there were 5 people who scored a 10. 1 of them was successful, 4 of them were unsuccessful. So hopefully you get kind of the idea of what this table is telling you. The total here would be your total number of successful people, and the total here would be your total number of unsuccessful people. So if you're thinking about cut score, right, you're going to want to look at this score distribution, and you're going to say, okay, what score seems to give me a good indication of where successful people would be? And you might just kind of eyeballing it say probably somewhere in here, right? Somewhere between 15 and 18 might be a good cut score to set. Because notice at 16 I start getting a very high proportion of successful people. So how do you actually pick the best cut score? Well, by definition, we want the one that results in the highest hit rate. So let's see how that would work. So how do you calculate the hit rate? Well, let's just try a few of these and see how it works. So let's start first with a cut score of 15. And then what we're going to do is we're going to fill out one of these contingency tables for these data. So we'll start by putting our actual outcomes of successful and unsuccessful on the two rows, and we'll make two columns for predicted outcomes of successful and unsuccessful. So how does this work? Well, if we set the cut score at 15, then that means we are predicting that scores at or above 15 will be successful. So that's how we measure our predictions. So what we need to do here is we need to count how many of those people are successful. Now note, I've already done the counting, and actual data showed us that there were 48 in the successful column and 49 in the unsuccessful column. So of those 48, how many were successful? Well, let's go back to the data and take a look. So if we set our cut score at 15, then everybody who scores 15 or higher is predicted to be successful. So how many actually were successful? Well, everybody in this column was successful. So the ones who scored a 15 or higher would be these 4, plus these 10, plus these 8, and these 12, and these 5, and these 3. Adding up those numbers from 4 up to 3 gives us a total of 42 people who were predicted to be successful and who actually were successful. Now we want to fill out this part of the table. That is, they were predicted to be successful, they scored a 15 or above, but they actually were unsuccessful. So again, let's look at everybody who scored 15 or above, but this time let's count those who are unsuccessful. So that would be these 5, these 2, this 1, and these 2. Adding 5, 2, 1, and 2 gives us 10 people who were predicted to be successful because they scored a 15 or above, but who were actually unsuccessful. Now, we can use the fact that there were 48 total successful people to infer that there were 6 who were predicted to be unsuccessful, but were actually successful. And there were 39 left here from these 49 who were actually correctly screened as unsuccessful. So now, once we calculate all the cells, we can compute our hit rate, that is the matches between prediction and an actual outcome. That's 42 plus 39 out of a total of 97, which gives us a hit rate of 0.835. Not bad at all. Well, let's see if changing our cut score to 16 improves on things. If we change our cut score to 16, we actually get this table. Let's real quickly go back to the original data and figure out how to get these numbers. Remember, we set a prediction of successful to be 16 or higher. We want to count those who were actually successful and those who were actually unsuccessful. So we'll go here. Those who scored 16 or higher that were successful is 10 plus 8 plus 12 plus 5 plus 3. And those who were unsuccessful is 2 plus 1 plus 2. So that gives us 38 who were predicted to be successful and were actually successful, and 5 who were predicted to be successful but were actually unsuccessful. Then we use subtraction to figure out who's left here and who's left here. Doing that, we take our 38 and 44, these are the matches, and we divide by 97. That gives us a hit rate of a little bit better, actually 0.845. So right now, having a cut score of 16 is better. Let's go up to 17 and see what happens. Well, if you do this exact same exercise, and you absolutely should do this yourself, you should get the following table. And here, when you calculate your hit rate, 28 plus 46 over 97, your hit rate goes down. It goes down to 0.763. So what that tells us is that setting the cut score to 16 is what gives us the best hit rate, and that hit rate was 0.845. So that's all for this lecture. We wanted to talk about what validity is, some of the ways it is measured. It's measured usually with correlation or something like that. What does reliability have to do with it? Well, reliability tells us the extent to which we have attenuated our actual correlation between some observed scores and some criterion, and so we can actually correct for that attenuation. And then finally, we talk a little bit today about how validity works in the context of dichotomous screening, which is very common in the sort of admissions type criteria or job candidate screening. So anyway, that's all for now, and we'll see you next week where we'll begin talking about construct validity. So until then, we'll see you next time.